In this lecture, we're going to discuss how exoplanets are found. And in particular, we're going to look at gravity and the Doppler shift, which is the core technique that led to the first discovery of exoplanets and the first few hundred exoplanets to be discovered. Gravity is the fundamental force in the universe that governs how masses interact with each other. Every object with mass exerts a gravitational force. That's even true of subatomic particles like protons and electrons, except their electrical interactions are many orders of magnitude stronger than their gravitational interactions. Newton's universal law of gravity said that every object with mass exerts a gravitational force, and described the force law. The strength of an object's gravitational pull is proportional to its mass, so more massive objects have stronger gravitational pull. And the other feature of gravity is that the strength of gravity decreases as the separation of the two masses decreases by the inverse square law. So if two objects are twice as far apart, their gravitational force goes down by a factor of 4. If they're 3 times further apart, it goes down by a factor of 9, and so on. Now, 1 over the square of a large number never actually goes to 0. So gravity is an infinite range force in the universe. And that's responsible for a lot of the phenomena of the universe and the very large distribution of masses in galaxies and even solar systems. In a gravitational situation, we talk about the center of mass. It's very rare to have truly isolated objects in space. Most objects in the universe are in systems, like solar systems or star clusters or galaxies themselves or even clusters of galaxies. So in all different scales, masses are close to each other, interacting by the force of gravity. In the simple situation of two objects, which could be 2 stars, or a star and a massive planet, or 2 moons of a planet, we describe the center of mass as being the place where the effective gravity operates from. So an object with the greatest mass will dominate the gravitational interaction around the center of mass, or the balance point. It's simple to think of this, like as in a seesaw or a teeter-totter. Imagine a small and a large child at different distances from the balance point, and where they would have to be situated to balance out their masses or weights. It's the same with the center of gravity. If 2 equal mass stars were in orbit of each other, their center of mass would be midway between them. As the masses become more unequal, the center of mass shifts towards the more massive object. So equal masses balance in the midpoint. If one mass is 10 times the mass of the other, the balance point is 10 times closer to the larger mass. And so in this analogy, we start to see the situation of a giant planet around a star, where the balance point will be much closer to the star than to the giant planet. This applies in the solar system too. The most massive planet in the solar system by far is Jupiter. And so the center of mass of the solar system is dominated by the orbital properties of Jupiter orbiting the Sun every 5 years. So the orbital situation of our solar system is dictated by the orbit of Jupiter around the Sun, happening every 12 years. At the distance of the Sun from Jupiter, the balance point turns out to be not between Jupiter and the Sun, but actually about the edge of the Sun at its limb. And so as seen from afar, because of the force of Jupiter, the Sun pirouettes about one edge every 12 years, caused entirely by Jupiter. So if Jupiter was unseen from a distance, we would still infer its presence by the wobble of the Sun around its edge every 12 years. And that's the basis for the Doppler wobble that was the first technique used to discover exoplanets in 1995. This is called a reflex motion in physics. So the gravitational pull of a massive planet, like Jupiter, is significant enough that it exerts a gravitational influence on the Sun. Remember, in the gravity law of Newton, the force on object A caused by object B is the same as the force on object B caused by object A, equal in both directions. This reflex motion can be measurable when the mass of the planet is sufficient to perturb the star, in this case the Sun, by a significant amount or a detectable amount. So we use this effect to look for exoplanets. Now, the wobble of the star turns out not to be visible. As mentioned, Jupiter causes the sun to pirouette about its edge every 12 years. If we were very far from the solar system, we might in principle be able to detect this wobble if we could take careful enough observations. But as seen from afar, the size of a star is indistinguishably small, blurred out by the atmosphere. And so there's no possible way of observing the wobble of a star like the Sun at a very large distance. Instead, we look for a Doppler shift caused by this motion, and that was the method actually used. So the wobble is inferred from a spectroscopic observation. And that means we consider electromagnetic radiation, or light, or the waves that are emitted by a star. Electromagnetic radiation is the source of almost all the information we get from the universe, till the discovery of gravity waves recently and the observation of neutrinos from various astronomical objects. For the history of astronomy, it's been the only way we learn about the universe. And for most of that history, the history of the telescope and the naked eye, it's visible light. Light, the color of light, is determined by its wavelength. And in the electromagnetic spectrum, wavelength and frequency are inversely proportional. All light waves travel at the same speed, the speed of light, 300,000 kilometers per second, 186,000 miles per second. Low energy light has a longer wavelength and is redder than blue light, which has higher energy and shorter wavelength. And this is part of the spectrum that applies in the visible range, but it extends to invisible wavelengths, both long and short, in the electromagnetic spectrum. So wavelength in electromagnetic waves is defined as the distance between two successive wave peaks, or peaks of the electric or magnetic amplitude, since it's an electromagnetic wave. The color of light is determined by measuring the wavelength. Red light has a longer wavelength than blue light. And in physical units, red light tends to be about 700 nanometers, where blue light is about 400 nanometers. The entire range of light visible to the naked eye extends over less than a factor of 2 in wavelengths, from the bluest blue to the reddest red. What happens when a source of light moves? Well, if we imagine the waves coming out from an object with the wavelength corresponding to the radiation we're looking at, whether it's red light, blue light, radio waves, X-rays, whatever they might be, we imagine concentric rings corresponding to the peaks of that light wave, moving out at the speed of light. The wavelength of light is inherent, it doesn't change. But if a source of light is moving, the motion of that source will affect our measurement of the wavelength of the light. In simple terms, as seen in the lower diagram, the motion of the source compresses the wavefronts in the direction of the motion and stretches them out or spreads them out behind the motion. And this is called the Doppler effect. Christian Doppler was a physicist working in the 19th century who first worked out this effect. Now it applies to every kind of wave, so it applies most familiarly in our world with sound waves or electromagnetic waves. It applies equally to any type of wave you can imagine. And we're very familiar with this phenomenon. You can hear it out on the street every time a fire engine passes by. As the siren approaches you, the motion is compressed and the tone rises. As the fire engine moves past you and moves away from you, the waves are stretched out and the tone lowers and the pitch lowers. This is the frequency going up and then down. This is the same effect we see in light. So the reflex motion of a star caused by the presence of a massive exoplanet can be measured in the light emitted by the star using the Doppler effect, which means it's an indirect method. You don't actually have to see the exoplanet at all. And as we've seen, it's very difficult to take direct pictures of exoplanets because they're hundreds of millions or billions of times fainter than their parent star. This is beyond all of the astronomical capabilities except in a few dozen instances. And even then, only the most massive or largest exoplanets at the closest distances can ever have a picture taken of them. So the receding motion spaces out the wave peaks and results in light being redshifted, moving away from the observer, and the approaching motion bunches up wave peaks, and the light appears blue shifted, moving towards the observer. Here's an animation illustrating the radial velocity method for detecting exoplanets. We start with the reflex motion of the planet around the star. As we tilt the plane to be equatorial, we see, represented in waves, how the light from the star changes as the star comes towards us and then moves away from us, blue and then red shift, in the opposite sense to the orbiting exoplanet. And this orbit repeats. And we end with the reflex motion view. Notice that in this effect, if we're looking straight down on the orbit, there is no Doppler shift, because the Doppler shift only applies to motion towards and away from the observer. If the orbit is entirely in the plane of the sky, there's no Doppler effect at any point in the orbit. It's undetectable. However, on average, exoplanets are going to be randomly oriented in three-dimensional space, so there'll be some measure of the motion. And in the particular case where we're looking through the equatorial plane and the exoplanet comes straight towards us and straight away from us, and the star does the same, we'll measure the full amplitude of the motion and infer the full mass of the exoplanet. If the star was completely stationary and not moving, there would be no measurable Doppler shift. In other words, a star with no exoplanet would not show this effect at all. If light from the star does show a Doppler shift, a periodic shift, obeying a sinusoidal variation over time, then the star must be moving in space, wobbling. And measuring that wobble allows us to infer the mass of the planet. So to summarize this lecture, we're using the phenomenon of gravity to infer the mass of an exoplanet orbiting a star. Any object orbiting another object means they orbit a common center of gravity. As the relative mass of the two objects increases, a small planet compared to a large star, the center of gravity moves closer to the parent star. But the star still wobbles or moves about that central point of mass, and that's called a reflex motion. Observed spectroscopically in the light from the star, that reflex motion converts into a periodic Doppler shift, following a sinusoidal variation. Motion towards the observer of the star, when it wobbles towards us in that part of its orbit, corresponds to a blue shift, and half an orbit later, motion away from the observer, when the star wobbles away from us and the planet is moving towards us, corresponds to a red shift. And so a star with a planet orbiting it will display a periodic red and blue shift, which can be measured, even though the planet itself has not been seen.